action?
Yes. So, X is an element of Lie algebra, and L is an element of a linear transformation on G. Why is this an action, first of all?
It has to be smooth and group action.
No groups. Thank God here. So it's just Lie algebra, right? So it's linear for sure, and also it should respect Lie bracket.
With what? What would the Lie bracket?
So you have some Lie bracket, right, on G, and you have Lie bracket on end G, which is just a commutator. So you would like to see that a bracket there.
Sorry, no, again.
No. So action. Right. So what do you have to check? Yes. So yes. So what do you have to check for an action of? So action is the following. It's actually homomorphism from G to this. Right. This is an action. Homomorphism means it's a linear map such that rho it respects a bracket, right? It means this. Yes. So what is V in this case? V is actually end G. Right?
But this acts on endomorphism of G.
Yeah, so this is actually end of G, right? So a bracket here, right? It is bracket here should go to some linear transformation of endomorphisms of G, right?
Okay. Okay. We're taking this as a representation of.
Yes. So end G is a representation. Okay. So if it's a representation, that bracket should go to bracket.
This is a representation of an element.
Yes. So that's what it means. The word action. Right? So this should go to.
What I couldn't relate was like to identify this as. Well, I identified it, but after that I didn't know what to do.
Minus y times minus y applied to x. So minus y applied to x. Yeah.
I got the identification, but after that, I take an element here, and I can rewrite it as an element here. But,
yes. So how do you write? So if you have A,
it was like. We take bases here and here.
Yes, okay.
And what here we have with respect to killing form or any form.
Just do dual basis, right, or something. Okay. Yeah.
And
yeah, something like this, right?
Yeah, because it's supposed that I have to take the indexes up, but okay, maybe I can do it here. And we take some on J.
Okay.
And,
yeah, I'm okay with putting indexes anywhere you would like to. Okay. Of course, Vadim might object, but for me it's okay.
Well, but we don't have an action of group on the face, so I guess.
So it's like that, like for each one we have one here.
Yeah, okay.
Okay.
But okay, this is good. We will use this. But before we didn't check yet that it is an action, right? So again, I would like to have this. It means that if I take this element, this is an element acting on this, right? So I apply it to L, right?
But you want to see like
It's the same as this applied to L.
like the Lie bracket applied to L. It's the same.
Mm-hmm.
The bracket. Like this. But how is that related with this representation?
No, it's not related to this, but at least we would like to first answer the question why this formula gives us an action. So that's what we're checking. So it's of course it's a linear transformation of this, right? So x applied to something is a linear transformation. Now I would like to see that the corresponding row respects the bracket, right? So this applied to L is the same as this applied to L. So it's almost the same as you wrote there, but you have x, y, and then so you have add x, add y applied to L. So like this, right, is the same as, so now you have add x, right, applied to L, and then add y. Add x, then add y applied to.
Yeah, I tried to write it actually. Yeah.
So like this, right? No. Like this. So first I apply add y, and then I apply add x. Maybe I have too much brackets. So what is this thing? It's row of x applied to row of y applied to L minus row of y applied to row of x applied to L. So first I consider this term, right? I apply row of y to L. I take this bracket. And then I apply add x.
Okay. Okay. Yeah,
Minus.
Like rewrite it like action y.
Yes. Minus add y, then add x, L.
And but we want to get that this is the same as like this. No. Yeah.
Yes, exactly. That's exactly. And that's exactly what I wrote here. Maybe you just yes, but minus. So you add x, right? Yeah. So let us look at here, right? I apply it to L, and then I apply this to L. How do I apply this to L? This is a commutator, so that's why I have minus the other thing. So it's I apply row, apply x, minus, apply x, then apply row. So that's how I get the other.
Okay.
But this is just Jacobi identity for commutator. Right?
Okay.
Jacobi identity. So what you forgot there is just
Yeah, like the
minus on the other side. This is Jacobi identity. Okay, so this is an action. Now I have another action on here, right? So we have this isomorphism that we wrote. We have another action in here. But what is the other action then? So we have this isomorphism, right? We described an action corresponding to this part of. Now we have another action corresponding to this part.
Yeah, like we had identity and like this. So we take
Yes. Yeah, this
we
is.
only have to use our I. Okay, as I remember, it was related with some bilinear form, and it was.
No, this is you need for isomorphism of G with G star. But you don't need it since you have you have action on G, you have action on G star, right?
Okay.
So adjoint action on G and adjoint action on G star, right?
Okay, so we have to act on our A and change it here. Just that.
No, so what I mean, so this thing is something like X tensor F, right? And suppose that I take Y and act on this, right? Then what is the result of this action?
Maybe something like
Yes. Just lead me through. So just need to lead me through, right? So that's how we define how algebra acts on the tensor product.
Wait, I8 F. No. Yeah.
Y apply to F,
Yeah,
right?
okay.
No,
I'm not sure because we will.
wait. So Y applied to F. So that's. Now you need to check what is. So this is just adjoint action, right? So it is add.
Y to F.
Yes. Well, just like this, right? Tensor F. Plus, and this is coadjoint, so this is X tensor. It's F, and then you apply add X, but minus X to it. To something that you. So this is a form, right? And this is another form if you start plugging something inside instead of this dot. But we need the minus here.
Okay.
And so we have this minus this. Right. So this is one action, is this one. Another action is this one. So why do they coincide? Okay, Valentina, could you help?
Yeah. Well, I don't know, but I used this.
Uh-huh.
So,
Okay.
okay. No, but what I did was we have this L
Right.
in the
Uh-huh.
and also we have this identification.
Right, that's what
So then
Abner got. Yes, okay.
So what I did was to first you make this action in L,
Mm-hmm.
and you try to write the matrix or
For
matrix representation for
yeah, so that's exactly what
this.
it is, right? Uh-huh.
Yeah, and then okay, I want to show.
Yeah, you can write in forms.
Okay, because
Okay, so yeah, thank you. You will help us out with
yeah,
some other problems.
I will
Yeah.
write it. So we have this action x on L.
Uh-huh.
It's given by this thing,
Right.
this arc. we want to see that this endomorphism coincides with this one, which was like, let's try to think if we can write this L as this way.
I suggest you to let me actually erase all this and start from the top so everybody can see. So this we actually check that it is an action.
So we apply this thing here.
Mm-hmm.
So first we add in the first component.
Yes.
Times the second part plus.
Okay.
So, right. So here we have action on this, which would be x.
Mm-hmm.
Because it's a joint action tensor.
Yes.
So now we leave the first term. We don't move it, and we add in the second part. But here we have the adjoint.
Mm-hmm.
So when
Co-adjoint. Yes.
Oh, yeah.
Mm-hmm.
So we need to remind that this adds by the negative sign.
Right.
So we would have something like some EJ. Okay, but here it would be the negative. Minus, I should have minus, because it's minus x,
Right.
bracket with this.
Yes.
So...
Yeah, you can erase plus there, put minus, and then...
Actually, okay, I wrote something like minus.
And then x with EJ.
And so we have in this part, something like this, evaluated here.
I think what you mean is... What is EJ though? I think it's just some other vector. All right.
This is in the dual?
Yeah, this is in the dual.
A functional?
Yes, okay.
So we have this. This is when we consider, first we make the identification to this space, and then we add. And if we do it in the other way, we act on L, we obtain this. So we can decompose this matrix with this endomorphism in terms of this decomposition. So now in this part, let's left-hand side. First we act, so we are doing action, and then we are making the isomorphism, this identification to, let's write it like this. So we need to take this and represent this linear map in this decomposition. So we would have, it's enough to think how is this acting in the basis, in the xi. Okay, he's calling xi, I'm calling...
Yeah, you're calling ei's. Yes, it's okay.
So once we do this...
And your aij's are lij's with the correct superscripts and subscripts.
The thing is, we will need to compute the matrix representing this. So it would be the matrix multiplication.
Yes.
The matrix representing the adjoint times the matrix representing L, and the same here.
Yes.
So we see this minus. This minus will be precisely
this minus here.
This minus here, and the first term will give us this part.
Yeah.
So we think in this matrix. This is the column, the I column of this. So we will have, let's say, Ki. This is the row, this is the column.
Yes.
So we need to think is precisely what we were writing here. So we have this, like E, K, this, right?
You may write add.
Let me write it.
Yeah, you're writing x commutator with ei as a sum over ek, a sum of k, right?
I mean,
ek and then some matrix elements.
Yeah, what I mean is this is the I column of this matrix. So
Yes.
row we will be summing over row, and this is fixed,
Mm-hmm.
and this is like this.
Mm-hmm.
This is a new vector which is written like this. These are dummy indices,
Mm-hmm.
up and down, so they are making the summation. So this is this part. So we write. Okay, okay, this is okay. Then I'm just going to write this thing. We will have something like this. I K, then L, K, J.
So, okay.
And then this, the basis would be like here. I put this,
Mm-hmm.
like this, and tensor. This would be the dual.
Yes,
power.
EJ.
EJ.
Yes. You're just rewriting this term,
Yeah.
plugging in what you wrote here.
Yeah. But this would be this prescription here.
Right. But that's what you exactly wrote. You
Yes.
have this term, you have this that you wrote like this, you plug into here, and you get this.
Yeah.
So minus. Minus you need to write this, right?
Yeah.
Now you would like to see what is EJ of x dot in terms of E case, E uppercase, right? So you have EJ x this, right? This is something times E k, sum over k. So what should go here?
Yeah. So we do the matrix multiplication.
Yes.
Again. So here.
So you know that this transformation is actually
Yeah.
also add. So this is add with corresponding indices.
So it will be something like this. Let me think. It would be like L. Let's say I. Let's say I. Okay. Then add K. J. And here would be G. Right. And so like this, I think. Probably.
Mm-hmm.
Yeah.
Um,
I'm just looking here.
yes. So I'm sorry. You have, but here summation is over which index?
I mean, this is summing here. This is making summation. This is
Yeah. So summation is over actually over all indices, right?
only
Okay. So overall indices.
Yeah.
But you okay. So but we need to continue.
Actually, yeah. The thing is, what I'm
We almost got it, right? Because here you have summation over k. K stands on in here low, and here summation over k that stands here. So it's matrix L multiplied this from the left and this from the right. Right? So this is actually. Let's continue. So this is sum over something EI tensor EJ. But what is this something?
You have to deal with the one.
Yeah, so this is this minus this.
Yeah, it's this thing.
Yeah, it's precisely matrix
Okay.
IJ's element of this matrix.
Okay.
Yeah.
The thing, what I was doing here was
Yes.
taking this commutation, and I was using this isomorphism and writing this in this decomposition. So I wrote this.
Right.
And we can see that this coincides
With the action that you started with as a G on G star. Yes.
Yeah, the question is that we already know that if G is a semisimple Lie algebra, it can be written in as let's say G1 to some GK. These are simple Lie algebras. And then we have to prove that if I is an ideal of G, then it can also be written as the sum of the simple Lie algebras. Let's say G1 to sim, I write up to Gi, and I is a subset of J, and where J is the same indices up to K.
Yes. It's not. So what are these indices though? Yeah, I guess this is what you mean is sum
Yes.
over I in J
Yes.
of Gi.
Yeah.
One, for example, might not live in J.
Okay. Okay. Yes.
You don't know, like, yeah.
Yeah. Okay. So this is what we have to prove.
Yes.
Now let's have a map by K with projects G to just GK. Okay. Now let us consider an ideal I, which is of G. Then we have the assumption that pi K of I is in the GK. Okay. So okay, now since GK is a simple Lie algebra, then I is either 0 or the entire GK. Okay.
Right.
Okay.
Because pi k of I is an ideal there.
I
So
is an ideal.
yeah. So and this one is an ideal in here. So therefore, it should either be 0 or coincide with the whole
Full
thing.
of GK.
Yes. Okay.
Okay. So now then we can write, let's say GK I is the same as GK of I pi K, which is GK. GK is a simple Lie algebra.
Okay. So this is why is that? So okay, explain this a little bit more.
Okay.
So first equality, why is that true?
Okay, first I is, let me just think on it. Pi K is G to GK, and pi K of I. Okay, because pi K of I, we are assuming that is the one, it can either belong to I1 to IK, sorry, G1 to GK minus 1, or it's in the, sorry, IK, or it belongs to IK. Sorry. Okay.
So who is IK? JK. GK.
GK is this. So I'm considering the
Yes.
last one.
So here is GK.
Sorry. Okay.
Okay.
So when I do this, so either I am getting the other ones, or it's just this one.
So you're saying it's either this or this, but why is that true?
Okay, because I'm starting with the assumption that my I, just a minute.
Yeah, I think that corresponds to the cases.
Yes.
Pi k of I is either what you said, right? So you have it's good to write down. So first you have pi k of I is GK, or pi k of I is 0.
Yes.
Right? So therefore, you have, so consider one of these cases. This will correspond to one of these cases here.
Yeah.
Right? So let's start with this one.
Okay.
So okay, maybe the idea is that everybody who solved that also discussed that. Okay, so everybody who wrote this number 2 in there, and not only those people, right? So we kind of work this together. So how to where are we? We say that okay, we have pi k is a projection from G to gk, right?
We need more things about if we take sum of this pi k and we get identity. And we use this fact.
Sorry,
And then
can
we
you...
get
Yes. Sorry, say it again.
if we take the sum of or around all the k of pi k, sum of pi k,
Yes, sum of pi k.
it's identity.
Sum?
What is sum of pi k? Pi k is some map, right?
Like direct sum?
Yes, the direct sum of
The projection of this idea in subspaces in the subspace.
I mean, if we take it's
Sum like a point-wise sum, right?
Then it's identity. It's obvious.
Yeah, sure,
So
sure.
we
Okay.
use this fact to and this fact and get the result. I think.
Yeah. So if you use this and this, so how to proceed though? I don't know how this actually helps you.
I was just going to write that at this point I can do just plus gk, or
Yes.
if it's not the other one, then let's consider some other idea. If it's, because I'm saying my pi k of I is gk. I is not gk.
Yes, I is yes, okay.
K of I is gk, but I is not gk.
Well, you never know, but
It may or may not be, so that's why I have another I prime here.
okay.
I is an ideal of G,
Yes,
the semisimple Lie algebra.
right.
So it can be using this projection map. Either, if I consider the projection goes to gk,
Right.
in that case there is this, and we may or may not have more here.
But from here to here, I'm not sure what. So you need this computation actually to get from here to here, right? Because I mean you need to show that gk is inside I. Then I prime will be an orthogonal complement. I mean, with respect to say killing form on I. I don't know. So anyway, so your so you need to show that gk is inside I, and this line is actually to do that, right? But we are in this assumption, right? So let me write. Oh, sorry. That maybe we'll need this. Yeah. So but why is this true? So I have gk. It's simple, therefore I can write this down like this,
Yes.
right? Now gk equals to pi k of I. So therefore it's gk with pi k of I.
Yes.
On the other hand, pi k of I applied to gk is again gk. So, right? So here I use that pi k of I is gk.
Okay.
So now let me use that pi k of applied to gk is gk, because it's a projection on gk, so therefore it is pi of gk, pi k of gk, and pi k of I. Therefore this is pi k, because pi k is a homomorphism of gk and I. But this thing, since gk is an ideal, lives inside gk. And pi k is an identity on gk. So therefore this is this. Right? So gk equals to this. But I is an ideal.
Yes.
So therefore this thing is inside
GK.
I. Now that's what we need. So gk is inside I. Right?
Yeah.
And therefore it means that we have this. Therefore it means that I is I prime plus gk, where I prime is actually an intersection of I and others.
E up to k
Yes, g I from 1 to
k minus.
k minus 1.
Yeah. And
Yes.
and inductively then we can do the same for k minus 1.
All right, so do the same. So but your I prime is an ideal inside this one,
Yes.
right?
No.
So you might use induction with respect to k,
Yes.
right?
exactly.
So therefore it says that I prime is a direct sum of some subset of g gi's,
Yes.
right? And then I is just add gk to that. So therefore we are done for this case. Yes?
Yeah.
But what if pi k of I is 0?
Well,
Again, you use induction, but how?
is it not okay? Maybe.
So what's the kernel of pi k? That's the question.
Okay, kernel of pi k would be. Okay, maybe I thought a bit naively, but I thought, okay, if it's 0, we can just move to the ones that are not 0.
But still, this is some case, right?
Yes.
We still need to prove that I of the form that we need. But this case is actually easier than this one. So again, if you just try to understand what's the kernel of pi k, this will give you everything. So what's the kernel of pi k?
Is the other g1 to gk minus 1?
Exactly.
Yeah.
So, but it just says that I is inside the kernel of pi k.
Okay.
So I is an ideal of something with k less than k that we fixed, right? So therefore, by induction assumption again, I is the sum of some copies of gi's.
Okay.
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 Yeah. Yeah. Very good. Yeah.
Okay, then the first part is we have to prove that ideal is or the quotient of any ideal or quotient of, I think ideal, I did wrote it wrongly.
Yeah. The commuting coincides with Lie algebras
Is
itself.
semi-simple. Okay,
Yeah.
so the ideal, well, just by the way we are writing, it's a semi-simple algebra.
Yes.
Okay, but then we have to prove that the quotient of the ideal is also semi-simple algebra.
Yes.
Okay.
Okay. That's another part, right? So did we have 3 parts in there?
Yes.
If it's the commutant,
deduce that any ideal quotient. Yes. Yes. Okay. Yes. Yeah. This is immediate, right? Because every ideal then is just some copy of simple ideals. So just by our theorem, it's semi-simple, right? And the quotient means what? I have some ideal I,
Yes.
and then I just kind of when I quotient, I erase those GIs that is in my ideal.
Yeah.
Again, this is some direct sum of some simples. So this clearly follows.
Okay, and the last part is just that.
Yes.
Okay, this G is, because it's semi-simple,
Mm-hmm.
GK.
Right.
Similarly here. So let's consider this part, G1, comma G1.
Let me erase this.
And so G1 is itself G1 because it's a simple algebra.
Right.
And by definition, it's non-abelian.
It's not.
Yes, so it's G1. Similarly for the other.
So not abelian means that this is not zero.
Exactly. Yeah.
But why it cannot be smaller than G1? Maybe something not zero, but still a little bit smaller than G1, but not equal. So simple means what?
That it's cannot be written as a sum of something. It doesn't have a radical.
So simple means it doesn't have proper ideals.
Yes.
But this guy is an ideal.
Yeah.
So if it's smaller and non-zero, it's a proper ideal inside G1. So it cannot happen.
Yes. Yes.
It is not zero because the G1 is not abelian.
It doesn't.
So therefore it should coincide.
Okay. Yeah.
Yes.
So with the rest, it's the same because we have a
Sure.
G1 to GK, and this is also G1 to GK.
I agree.
So we get a G because we'll just get the GIs.
Yes, but you only say that GI commutant with GI is GI.
Yes.
But you also need to say something about GI with GJ.
GJ.
Different indices.
It will be 0
Sure. Why?
because they are simple algebra and they are different ones.
No, the right wording here is that the direct sum.
Okay.
By definition, direct sum of Lie algebras means that if you take an element from one summand and an element from the other,
Zero.
the commutator will be zero. Lie bracket will be zero. Yes. Okay. Yeah. Thank you very much.
I have a question about this.
Yes.
How do you say conversely if G, the commutant of G is equal to B, then we can say G is semi-simple?
You're saying that if I have this,
Yes.
then is it true that G is semi-simple? So if G coincides, so I would like to see something, say something about the radical, right? So if I say that radical of G is 0, then it's semi-simple, right? But if I say, so the radical of G is 0, so I would like to deduce from this maybe this, right? From here to here, it's clear, right? Because this is solvable, right? And D1 of solvable is again the Lie algebra. So if I keep taking D's, it will never go to 0, right? Except if radical G is 0 at the very beginning, right? But is this true if I have this? Not so clear. Maybe I don't know. Maybe not. I cannot say right away. So maybe a good problem. Yes. But not sure. I think it's not. I think it's not true. But maybe I'm wrong. So I don't know.
What was the question?
So the question is that converse statement, is that true? So we proved if G is semisimple, then the following happens. So the question is, suppose that I have some Lie algebra for which this happens. The question is that if it's semisimple or not. Okay. I will think about that. Somebody wanted to, so you wanted to say something, right? Yes.
Use this.
Yeah. So some.
This,
So let's erase all that.
actually identity map. We use
Yes.
these facts and
So this is just a point-wise sum, right? And
And,
you,
we have actually just the Sinchit aspect is this is GA or 0. And so now I and I is this and then use this thing. And next, by the second fact, this guy is GI or 0. And then I is this. Then we're done the first.
Yes. Okay. Now let us think if you're tricking us or not. So let's see. I is an identity of I. That's of course true. Then you have pi I. Sure. So pi I is either g of 0. So from here to here, you know, something is funky. Because this, again, this, as I said, this is a sum of APIs. I would rather call it like this. So this is just point-wise sum. So from here to here, I should say something. Right? So this is just point-wise sum of maps. Right. How do you prove that this is direct sum?
Because the image of this pi I are not intersect.
Images do not. So it's actually for any subspace that's true as a vector subspaces, right? Then pi I of I is an ideal inside the G, right? Right. So seems like yes, seems like this is okay. Yes, so right, images do not intersect. Yeah, I don't know.
Just to prove that.
I didn't catch you on something. I didn't catch you on cheating here, so let us count that for now. Yeah, okay. That's kind of okay. Very well. So this is it. Let's do 3.
But before I just want to ask what I was doing here, because my proof was like this. So I take an idea, I, and I was trying to make intersections with each GI. I mean, I don't know if you tell me if this is correct or not. I was doing something like this. This is G, but this is the direct sum. This is G. So then I was writing I like direct sum of the intersection with each GI, but I don't know if this is wrong. And then I was just saying that this is an ideal inside each GI.
I think this is actually wrong.
Wrong?
Because think of just C2,
Okay.
right? And you have so you have or even let us take R2, okay? Just to draw it on a board. So you have 2 directions, all right? And so X, R, so this is E1, this is E2, right? And you have this.
You don't necessarily intersect the axes.
Yes,
Oh,
yes.
Right. Because I think I didn't finish this problem. I just have like ideas,
Okay.
and like I feel like
That's the best time to actually go to the board, because that will make you,
yeah.
completely understand what you did,
That's
what you
why
did.
I want to
Yes.
think where to start. The thing is, G is semisimple.
Right.
So we know this is G1.
I think it's better to just take case 2.
Sure.
Yes.
Let's take K crystal. It's a good suggestion.
Make everything.
Okay.
If you
Can
wish.
consider
If you
that?
wish. If you don't like it, it's okay. What?
Because because what I was thinking, I think about 2 things. But let me just say the first one. First thing.
And these 2 things are not G1 and G2, right? Anyways.
Okay. So we need to consider the phi in endomorphism of G that are equivariant, which commutes with the adjoint action.
Okay.
Adjoint representation. So we will have something like this. Right? For any x and G.
Yes.
And then I was okay, this is going like this. And to n. Okay, so we can think about the restriction of this linear map in each simple component.
Yes.
So first, I think this is true if I take phi applied to GI. This must be contained in GI.
It is true, but something that should be proved.
Yeah, okay. Okay, why this is true? Suppose this is not the case. Suppose that there is someone, x here,
Yes.
such that it is not contained in GI. So it's in some other component, probably. So then we apply this formula. So take this x, let's call xi, is the same as this. Okay, and we are assuming by contradiction that this is in some other component.
Okay.
Say, not
Say
here.
GJ.
Gij.
Uh-huh.
And this is true for all elements that I plug in here.
Okay.
So then, in particular, if we put gi here, gi here, the right hand side would be 0. This right hand side would be
Something
0.
something
because
from
they
GI.
are-
Okay. Yes.
Something from gi. So this would be 0, and this part, it would be just someone from gi x. This is what I mean. Something like this. 0 for all gi. That would be true. So the thing is, then what you will have. Just a sec. Okay, so you look here. This element, it's in Gj, and for any element in wait a second. Oh no, I think I have a problem there. Okay, because what I wanted to obtain was having some information about the center of this component. We know that the center must be trivial, something like this. So
Yes. Yes.
yeah, I wanted to conclude that this cannot happen. Like, we cannot have a non-trivial element for which this is 0, because for any element here, it would be commutative, the bracket. So it would be in the center, but this the center of J is trivial.
Right.
That's what I wanted to obtain, but I don't see it clearly now.
Yes. So if you have this, all right, therefore.
I mean, okay, this is in GI. Plug any GJ here.
Right. So
GJ,
yeah.
this is 0. Phi of 0 is 0. For any, it doesn't matter which thing we plug in here, this will be 0.
Yes, I
bracket.
agree.
So
I agree.
phi of this xi would be in the center of Gj. But this cannot be the case.
Yes.
Because Gj is simple.
But again, why is it in the center? Sorry. So you, for any G, I.
Gj. This is in Gj. I'm assuming this is in Gj.
Right.
Then I make the commute.
But if you plug in something from Gj to here,
Yeah.
it might not be might not be 0 though.
No. But if you look in the left hand side,
Right.
this x is in Gi, and here you're plugging someone from Gj. This is 0 because they are non-intersecting ideals.
Yes.
They are-
Yes.
Okay, so of course this is a linear map. The image of 0 would be 0. This is 0, and this means that phi of xi commutant with Gj, any Gj,
Yes.
this is 0. So
Yes.
this is in the center of Gj.
Yes. But it means that phi of xi is actually 0.
Yeah.
So xi is in the kernel. Right. Xi is in the kernel. But I would like to argue that phi has no kernel. Right? It actually is this true? I don't think it's true. For example, I can take 0 map right? And it
I
will.
think that's
Did I say like inversible there? Not inversible. All homomorphism. So actually, yeah, sure. I can take zero map. Of course, it can be zero map.
okay.
Mhm.
For this, in this way, I don't know now, but what I was thinking
Mhm.
was trying to reduce this linear map in each component, like in G1 to G1,
Mhm.
in each of these, and then trying to use in some way the Schur lemma,
Mhm.
something like this.
But
So-
I'm sorry. So you supposed? I think it's clear now because phi of xi. So what you was trying to do is to prove that you cannot go outside of gi.
That's what I want to do.
But phi of xi is you don't know, you don't need this, right? So then phi of xi is 0. Suppose it belongs to some gj, right? Then it's 0. So you actually didn't go outside of gi. So you actually proved that.
Okay.
Yes.
Okay, so this is true.
Yes.
And then what I wanted to do was so we can, yeah, so we can consider the restriction to GI, this linear map.
Mhm.
So we have GI to GI. We can consider this. And then also we have the adjoint representation acting on each of these.
Right.
Actually, I think because if we take any element, it's a direct sum of all these things. The others from GJ, different from GI, they are doing nothing. They are killing in the bracket.
Yes.
So you can consider that here, in the adjoint representation, you're only acting by these things, elements here. And then what I wanted to do was to...
So you would like to prove that it is either it's just a multiplication by some number, right?
Yeah, because this is an irreducible representation.
Yes.
I can say that.
GI is a reducible representation
Because
of
this-
itself as an adjoint representation.
Yeah,
Yes.
because you cannot have invariant subspaces here.
Yes.
This is simple.
Because
so
it's simple.
we can apply the Schur's lemma,
Yes.
I think. So then, by this lemma, you have that this map.
Mhm.
I don't know. It's either 0 or a scalar multiple of identity.
It's just a scalar multiple of identity. I mean, you can multiply identity by 0, you will get 0 map.
Okay,
Yeah.
you're right.
Yeah.
Okay, so then we have restricted to this. It's a lambda identity
Yes.
in GI.
Yes.
Okay, so but in principle we have something like
So we actually solved it, right?
Oh, okay. I'm not sure of what I was doing, so I wanted to ask.
Mm-hmm.
Then the whole phi would be the direct sum of each of these maps,
Mm-hmm.
right? So maybe
So what is direct sum of a
Is-
map? I still don't understand. So right, it's actually just a pointwise sum if you
Yeah,
right?
yeah.
Okay.
yeah. So and so you have in the cases for which this is trivial,
Mm-hmm.
you will have like projections.
Mm-hmm.
These are just like projections. Maybe in some components you don't get the whole GI.
Yes.
Maybe in some others you will get it.
Mm-hmm.
Okay, that's what I could do.
That's I think
I don't know
you
if
solved
that's
it.
what you, okay, and the other, I want to say...
So let me just illustrate it again. It's always useful to draw blocks of matrices.
Mhm.
So if you just have some linear transformation from here to here, you have blocks corresponding to different GIs.
Okay, I think it should be something like...
Yes. And so this block corresponds to your phi restricted to G1,
Yeah.
and it goes to G1. Not really. So this whole row of blocks, right, corresponds to phi restricted to G1. But you proved that you cannot go outside of G1. So therefore, all these blocks are zeros,
Yeah.
and the only thing is phi 1. And here also zeros.
Yeah.
So you have only, so by proving this, where was it?
Kind of Jordan blocks, generalized Jordan blocks, because these are not necessarily.
Yeah. Yeah, so when you were proving this, you prove that your off-diagonal blocks are zeros. Right? Off-diagonal blocks correspond to, transformation of vectors to go to the other GIs. But when you applied Schur's lemma, you say that each of these blocks is identity times some scalar. And that's what happened.
Okay.
And so you just described all metrics. So that's how you kind of got the whole problem, right? So describe the whole matrix of transformation.
Okay.
Yes.
Okay. I want to say something more.
Sure.
I was thinking more.
Yes, okay.
Other way to think about this. Another way to think about this problem is to think in terms of the first problem, the action on endomorphisms by G, the action on G of G.
Okay.
So we want the maps phi such that they commute with the adjoint. So we want to have something
Yes.
for all x here. So it means we can think in that action, this is 0 for all G in terms of the first problem. And then I think then we can say that this phi, it's in the centralizer, what you defined today. Am I right? I mean,
Yeah, but centralizer is subalgebra of G, though. It is centralizer of what subalgebra in which algebra you should
okay.
specify, right?
This G, we can think there's an isomorphic algebra inside endomorphisms of G. Because the adjoint, the image of
Yes, I agree.
this is in endomorphisms.
And this ad has no kernel, so G is subalgebra and G of G, right?
Yeah, so you have each element here is represented uniquely represented by someone here, and a linear map here. X is here. So is this element? So you are.
Yes, and phi is in G, right?
I mean, you have something like. Yeah, like where did I? Where?
Right. So you're saying that all homomorphisms, right, that we would like to describe, they form a subset in here, such that this happens.
Yeah.
But this is exactly our definition of centralizer. Yes,
Yeah.
I agree.
So this is centralizer.
This is centralizer, yes.
Yeah. Oh, and also, okay, wait. Oh no, because in this, I was also thinking about the last problem, that the derivations are this G, in the image of G. So in this case, if you consider a linear map, which at the same time is derivation, it must be trivial.
Linear map, which is derivation. No, derivation is linear map by definition.
Oh yeah, but I think in this problem, if you consider this phi,
Yes.
big phi, if one of those maps are derivations, then they must be trivial.
You would like to see that
I just
that your map phi is, yes, your map phi is derivation. Is that what you would like to do?
Yeah, if we consider some of them, I don't know who are they, who are they, but if some of them are derivations, that they must be trivial. That there, if some of them are the ones that are derivations, they must be trivial.
Trivial in the sense that they are in the image, right? So if you take again, if you take endomorphisms of G, and you consider some derivations in here, then this is in the image. This is inside G actually, right? But how do you want to use that? For that problem, I'm not sure.
G is semisimple.
Yes.
G is semisimple. So
Yes.
can I say about the center? If you want?
Yeah, center is trivial, sure.
Center is trivial. So these derivations must be trivial.
No, derivations of semisimple are exactly this. Add G. So these are all derivations. They are not trivial. So all maps like this are exactly the derivations that for semisimple algebra. That's exactly what's written here.
Okay, yeah. Okay, no, I don't know what it is.
I think you're using like a gun for a knife fight, or even fist fight. Yeah.
Okay, no. I was also thinking in the exact sequence again that you were explaining. Something okay, no, I don't know. I was thinking something, but I don't know.
Yeah. Okay. Maybe you can remember, and we can talk after. Yeah.
You want to trick?
Checking it to solve.
You would like to cheat again, right?
So I will not give the full proof, but just the idea. And another thing is, I think, for simplicity, we just consider just two components, and we have a function, linear map from G to G, which satisfies our condition. This commutator is add, and we just assume that f acts on maybe this is xy. Linear map.
So F1. Who is F1?
F1 is the first component of, or you can say that it is the pi 1 component. Or I don't know.
Let's talk about this. F1 means the image of this is in G1. And F2 means the image of X is Y.
Okay.
And we write down the condition that it must, or maybe first should write something like that. So, it's section EX PY. And now just computes the commutator.
But where is your F though? Okay. Here it is. Okay.
This I picked on x plus y. I will just write down the result. It will be f1 ax b and f2 ax b y. Same thing. And another of commutator is
Yes. Yes.
And now these two guys should be same thing.
Yes.
So this part should equal to this part. But here it depends on b, but it's not. So and because of the g is a semi-simple, so f1 should not depend on this. And we just analyze the dependence of this f1 and f2, then we get the so the rest part, I think everyone can finish by themselves.
Yeah. Yeah, that's not cheating. That's just the same thing, kind of, that Valentina did.
So
Just
direct.
Just another way to write it. Yeah. When you say it's b does not depend on a, you are making zeros of diagonal blocks.
Then f1 does not depend on the second component of itself. So
Yes, of diagonal, and then
that f2 is same.
and then since it's simple, you still need Schur's lemma again to say that f1 is scalar multiple of identity. Yes. Very well.